the types team. So, new team node, share, read everyone, right, I guess. Right, pasting the link into the meeting chat. And also, I guess just in sort of. Cool. So today's topic is the new solver in Rustc and how it works. At its core, what we do is we have some goal we want to prove, and then the solver recursively proves that goal. And like a goal is an environment. So assumptions we have, like in a function with a t-clone bound, the assumption would be t-clone, and the predicate, yes, we can. Is it good? Or one larger still? All right. So we have the environment, which is stuff we assume to be true and will be proven by the caller or by the user of this item we're currently in. And then we have the predicate, which is the thing we are actually proving, which is one of those. So the most important one are trait clauses. So stuff like the type foo implements a trait bar with the following generic arguments. And we have these, and then also projections, like projection clauses, which require that some projection, like back of U32 as iterator output, is equal to some type. And projection predicates I use both if you have a bound, yes, rather than HackMD, if there's a bound like projection foo t trait with so equals U32. If you have that function, if you use it, you have to prove that TS trait circ is equal to U32. And also, when we normalize types, we also use projection clauses. So if we have,
is it easy for you to place the window where you're writing the HackMD?
Yeah, I guess I can do that. Yes, that makes sense. Yes.
For recording purposes, yes.
Yes. So if we have like of, I don't know, U32 straight output, normalize that to back of whatever string. That also uses projection predicates. And so projection and trait predicates are the most important ones and also the most complex ones in the solver. So if you have some trait predicate you want to prove, you enter the solver via evaluate canonical goal. The way you call it evaluate canonical goal is actually by, oh well, where is it? I didn't merge the most recent PR yet, so that's annoying. Is by evaluate goal, which does canonicalization for you, which we'll get into later, hopefully. We can just ignore canonicalization for now. So anyways, evaluate canonical goal does a bunch of stuff to do with conduction, which you can ignore, and then calls compute goal. Compute goal is the core of the actual logic of the solver. So in compute goal, we have a match on the kind of the predicate. So like what we're proving, whether it's a trait goal or a projection goal. And then we just recursively call the function to prove exactly that goal. And I guess let's just start with trait goals because they are cool. So proving trait goals happens in 2 steps. We first search for candidates, and then we merge candidates. So a candidate is, or like we have different candidates for ways in which you can prove goals. So these are defined in assembly. And we have like a candidate has like a source where like the way in which we're proving something, which can be a impl written by the user, an impl defined like internally by the compiler for stuff like sized or special traits like discriminant kind, pointy, unsizing and stuff, I think. So that's for stuff where the impl is not written in a library, but instead generated by the compiler. Then we have param-env candidates. These are assumptions from the environment which we are using to prove our goal. So instead of is clone, we prove that t implements clone using the t implements clone bound in the environment. And then finally, we have alias bounds, which if the self type is a projection and that projection has a bound itself. So for trait, all associated types have to be clone. That's checked when we write the impulse. So whenever we use that associated type, we can just assume that it is clone because that's proven when we check whether the impulses are correct or not. So my mouse is hanging right now. Oh, everything's hanging. Do you still hear me, or did I just break my computer?
You're fine.
Okay, my computer is not fine. That's
We'll just yeah.
So that's a very beautiful screen. I can't do anything else right now. It works again. Beautiful. So what proving trait goals does is it assembles candidates. So it goes through all the ways in which you can prove stuff and checks whether these ways apply to our current goal. We don't do that if the self type is an inference variable because we can. That's like, yeah, we just don't. And then we assemble candidates after normalizing self type. That one's a bit more involved. We'll get to it later. Then we assemble candidates from impulse, which is here, it loops over all impulse, which are defined by the user, and check whether that impulse can be used to prove our current goal, which, well, if we have a trait goal, that means we check that the impl header unifies with our obligation, and then check whether the where clauses of the impl apply. So we can look at that code again. No, we should actually go to trait goals. Consider impl candidate, exactly. So we have performance optimizations, which are always cool. But then we take the impl, replace the parameters with inference variables, and then equate the trait graph from our goal. So if the goal is, I don't know, vec of t clone, then we equate vec of t clone with vec of question marks, like with vec of an inference variable, so vec of question mark 0 implements clone. And that then would constrain question mark 0 to be the generic parameter t. And then we also have to prove the where clause of the impl, which for the clone impl for vectors would be that T is also clone. So here we have the where clause of the impl, and then we prove both the where clauses and nested goals from equating stuff, which we emit for projections and can also hopefully ignore. And finally, we check whether all the nested goals hold, and then return the result of that check to the assembly context, which, if the impl could apply, adds it as a candidate to our list of candidates. Then that's impl candidates. For built-in impl candidates, we have a large if chain for all the different traits, where depending on the trait, the built-in impl is slightly different. So I guess we can look into a few of those. So for auto traits, the built-in impl, wait, where's auto traits? Is it already implemented? I hope it is auto trait. So for a type implements an auto trait if all of the fields implement that auto trait. So what we do is we collect all the constituent types for this type. So I guess I could write an example. Auto trait impl Rust for field string field. And then if we have a foo send goal, the constituent types are string and back U32. Then finally, we check whether all the constituent types also implement the same trait. So that means check string send back U32 send. So that's the built-in the code for auto traits. Then back to assembly. We also have for sized, where we again look at all the fields, check whether each of the fields is sized. We have copy clone for stuff like arrays and tuples, or like that. And yeah, most of these are look at all the constituent types, check whether the constituent types recursively implement the same trait. But the exact field types we actually look at are slightly different between built-in traits. So for example, the size check for references doesn't look into references, but auto trait do look into references. So we have to treat them slightly differently. That code is in structural traits, where we have it for auto traits, for sized, for copy and clone. So that's built-in candidates. Back to assembly. Then we have candidates from the environment, where we go through all assumptions in the environment. So in looking at this example, is here in this function, there are actually two there are two assumptions in the environment, one that T is clone, and the other one is that T is sized, which is implicit. And we would just iterate over them. And for each of the assumptions, we call consider assumption, which Is that already implemented here?
Yes.
Beautiful. But I can't find it. Yeah, cool. So we're actually equating the trait refs. Okay, that works. So yeah, we check whether the substitutions are equal and the trait is the same. So that's cool. And then any nested goals from equating those types are again evaluated, and we take the final result as the confidence in this candidate. So after, I think these are the most important candidates, aren't they? Yeah. Param, then alias bound just looks at the self-type, gets the item bounds of the self-type. It again use consider assumption for that. And object bound is kind of the same, I think. And so we now have all the different ways we can prove our trait goal. And we also have like the result when we use that candidate. And that result can either be that we just can't use it at all, so an error. In that case, we don't add the candidate. And if we can use the candidate, it can either be ambiguous, so we don't know whether it applies, it might apply, it might not apply. But even if it's ambiguous, we can still constrain inference variables. And the other option is that we know that this candidate can definitely be used to prove, like this candidate definitely proves our goal, while also constraining inference variables. So the Ztrait-solver can constrain inference variables if we have the following example: Rust Ztrait-solver, some generic parameter, import for u32 for i32, f1 So if we have this function and then call impulse foo with i32 and an inference variable, then in the Ztrait-solver, because there's only one impl candidate, and that impl candidate requires u to be u32, we say, hey, there's this candidate. It definitely proves that foo is implemented, but it does require that this inference variable is equal to u32. So when we now have these candidates, there can sometimes be multiple ones. For example, if you have both a impl written by the user and an assumption from the where clauses. These can overlap, they can partially overlap, or also if the input has inference variables, there can be two inputs which apply by constrain the inference variables in different ways. And the way this solver deals with this is somewhere in this file. Is in compute trait goal. And it's in merge trait candidates and discard reservation impulse, which is not perfectly implemented, but the way it works that so in the old solver and the way it's currently done is that it simply prioritizes some candidates over others. If we have one candidate from the environment and one impl candidate, we currently always prefer the candidate from the environment if that candidate holds. So yeah, that's this behavior where if we have multiple candidates, we try to check whether we can remove some of them. And in the future, we will also merge candidates if they have the same result. Well, if they have the same constraints and the same result. No, actually, only if they have the same constraints. So if we have one candidate where we know it holds and one candidate where it's ambiguous, but both constrain inference variables in the same way, then we can still just say, hey, this holds with these constraints on inference variables. So yeah, but right now it's not implemented yet. And it's also not implemented in the old solver, so we can wait with this. This is how trait goals work, where we go through all possible ways something can be implemented, check whether these ways work by recursing in the solver and proving like nested goals. To prove nested goals, if there are multiple of them, we use evaluate all. Evaluate all in a loop tries all nested goals as long as these nested goals make some sort of progress. So if one of the goals constrains an inference variable, that can help another goal succeed. So we run a loop until either all goals succeeded, one of the goals definitely fails, or we end up with ambiguity because we tested all goals and no goal changed any constraint, any inference variables. And in that case, we just say, hey, it's still ambiguous. We don't know. So that's trait goals. The other other complex one are projection goals, where again, if we have such a goal, we call compute projection goal. Compute projection goal has one. Is it a hack? For performance, we only do most of the work if the expected types of projection goal is some projection is equal, that's not an assignment, that's equality, is equal to some type we know about, or well, to some specific type. But what we can instead do is we check whether there's some type that's equal to this projection. And if we call, if we recursively compute that, what we simply do is we just normalize the projection and then return the normalized type as a right-hand side. So we pretty much check, hey, is the right-hand side, so the expected type, is that completely unconstrained? Like, does it not occur in the projection itself? And if so, we again assemble candidates and then merge those candidates. And if the right-hand side is not just an inference variable, we recursively call that goal with the right-hand side replaced with an inference variable, and then equate the output from that recursive call with the actual expected right-hand side we have here. So that's only for caching, because there can be quite a lot of these projection goals with different expected types on the right-hand side. And computing projections can be, it can take a while, because we tend to prove nested goals, which is very costly in some cases. So we again have the shared code between, well, we have the shared code between traits and projections, where we assemble all the different kinds of candidates. And the only thing changes is how exactly different candidates are considered. And for projection goals, let's look at the impulse quickly. It starts the same way as trait goals, where we unify the impl headers, check the where clauses of the impl. But after we do that, we also check, we also look at the associated type itself, which is quite a lot of code to deal with the fact that we can like inherit associated types from another impl or from the trait definition. So if we have associated types, if we have trait type s equals 32, and then we should be able to write input trait for, and I think that this works. I'm pretty sure it does. Let's actually test it. Ah, so that's unstable. Well, that's annoying. But anyways, it does exist as a feature. Does it exist as a feature? I hope it. Why is that unstable? Interesting. Yeah, but for this, we do a bunch of mapping substitution, like mapping the arguments for the impl from the impl we're using to the impl from which we're getting the associated type. So that's what we're doing here, which takes a bit of space. Then we also deal with the fact that can not only, like we also reuse that code for associated constants. So that's there. So you can't use them in default impls. Yeah, I guess that makes sense because otherwise you would have to manually write the impl again or the method if the associated type is changed. I don't know. But yeah, I guess it's a design question. I don't care. So yeah. All right. So so we look at the associated type and we get the associated type and then equate that associated type with our expected type, which, because we only get here if the expected type is an inference variable, we know that this cannot fail. And then again, we return the result. And for some built-in traits where we don't have associated types, we just bug. So that's the rough structure, which is pretty much like the same between trait and projection goals. And now that's cool and all, but there are some issues. The biggest one is cycles. So if we prove a trait goal, we may encounter a cycle. These cycles, how do I go about it? So a nice example might be a struct foo. Well, actually we have, yeah. Let's make it a linked list. Enum list. T null cons T box list T. If we now want to check whether list of U32 implements send, we use the built-in auto impl, which requires that all fields of nil implement send, and there are none. Then we require U32 send. And then we require box list U32 send, which requires list U32 send. And that is a cycle. So the way we deal with cycles depends on the kind of trait we have. There are inductive and co-inductive traits. right now, the only traits which are co-inductive, which means that, like, to simplify, it means that they allow cycles. There's, in the Rustc dev guide, there will be a section about it once that's merged. So where is, okay. So co-induction. Look at the dev guide. So what we do is write, like, all of that cycle detection happens exclusively in evaluate canonical go. So we detect cycles. We also deal with overflow. So if there's a trait goal which just recurses forever without ending in a cycle, we have to detect those, because otherwise we get a stack overflow in the compiler, which isn't great. And all of that happens in this one function, an intercanonical goal. So when we first start to try and prove something, we check whether it's in the cache. So we have, well, we will have a global cache and a provisional cache. The provisional cache is the list, or well, a hash map of all goals where we're currently still in the process of proving them. So if something is in the global cache, we would just return, hey, that's the result. We don't have to do anything. And then we check whether we're currently computing it. So it's either directly on the stack. So we maintain a stack of all the goals, which we prove we're recursing. We push something on the stack. Or it's another goal which indirectly depends on something on the stack already. So we look into the cache, and if it's not there, we check for overflow, put it in the cache, put it on the stack, and continue proving it. If it is in the cache, we do weirdness for caching. Oh, well, we do. We have to be careful because we now depend on something in the cache. So the result we get might not actually be the final result, because there is, like, the dummy result we have stuff on the cache isn't actually the final result. For this, read the section on co-induction, or we have another explore session about co-induction, because that's involved. Yes. So we, on a cycle, we then check whether it's co-inductive. If it is, we tend to return, okay, this nested goal holds, or like, you have a cycle, that's good, your goal holds. If we are not co-inductive, we know that the cycle would just result in, well, the cycle results in overflow, because with induction, cycles are not allowed. So that's one thing. So dealing with co-induction, dealing with cycles is done in this function. And then the final big concept needed for the solver is canonicalization. So the idea of the Ztrait-solver is to reuse, like, if we've proven a goal, and then we have another goal which should result in the same result, ideally we just take that from the cache and don't recompute it. And for this, we don't really care about specifics, mostly about inference variables. So if we at one point prove that U32 implements trait of some question mark 0, so some inference variable, and then later we prove we have to check whether it proves it for another inference variable. Ideally, these two they reuse the previous result, because while trying to prove them, the exact identity of the inference variable doesn't matter for us because we have no information about it anyways. So what we do is, instead of proving that, these two instead prove, like, does there exist any type so that U32 implements trait with that type. And potentially the solver then says, yes, but T has to be U32. And going from inference variables to this thing with an existential bound, that's synodicalization. Cool. So is that all? Well, apart from going in depth into either canonicalization or conduction. All right. Are there any questions? All right. I'm not sure if in the recording you can see Zoom comments. So let's just copy paste the question into the HackMD. So, and also make the HackMD large. So, if that's the case, then true. Currently we do eyes, but what will happen is, like, that pretty much means we have input trait A for U32 and input trait B for U32. Like, we have these two impulses somewhere written by the user, and that's where during assembly we assemble input candidates, and here we go through all relevant input candidates, and if the input candidate could apply, we add it to the list of candidates. So, like, we assemble input candidates, and I think, let's just say all other assembly methods don't add any additional candidates. Then assemble and evaluate candidates. So that one will return, let's give those impulse name impl A, impl B. That one will return candidate with source impl A. Oh, it's annoying. Impl A, and then result yes, and candidate source input B result yes. So we have multiple input candidates here, and with those multiple candidates we then call merge merge trait candidate something. Where are you? Merge trait candidates. And if there are more than one candidate, we try to filter them in some way where we mostly drop impulse. Yeah, I guess let's do that. input result, yes. Constrain question mark 0 to U32. No. To A. Okay, that's ugly. I guess yes. U32 equals A. And then yes. Schmark 0 equals B. So we have two candidates and both have different constraints. And here we won't be able to drop any of the impulse because they're equally as valid. So what we instead do is, wait, why isn't it implemented already? So we then get to this fix me and would return ambiguity. So there are, yeah, exactly, that's where we are. There are two ways we can return ambiguity. Either we just say, okay, well, in this case, there's only one, but you could imagine if you change it. So merge trait candidates and reversion impulse, then it returns ambiguity with no constraints. If you instead had input trait of back of A and back of B, and then you would constrain the inference variable to vectors of types. And in the current solver, we would also return ambiguity with no constraints. I expect the initial implementation of our solver here to also return ambiguity. But like in the longer term, you can definitely imagine that we instead say, yeah, this is ambiguous. But we know question mark 0 is back of something. So in that way, you would still make progress even though there are multiple candidates. But well, for now, nothing is implemented here. Is there anything else? Canonicalization. Okay. Well, no, I didn't have any other plans. I am done. So for canonicalization, I have a HackMD, but that one's okay. How do I actually talk about canonicalization? So that's another section, canonicalization. First of all, there are Rustc dev guide sections. Your server section is XXX, so PR. And there's also the talk section about it, which talk is this. So the idea of canonicalization is if you have an input which has like mostly inference variables, but also like placeholders. So placeholders are universal variables. For example, when you equate higher ranked function pointers, while equating them, you replace the variables bound by those binders, the bound variables, replace them with placeholders to check that the equality holds for all possible lifetimes. And both the placeholders and the inference variables, like there can be a lot of different ones, and each inference context has its own, which are completely unrelated between them. So what we want to do is we want to say, no matter what the inference variable is, this works for all inference variables. And the way we do this is by converting inference variables and placeholders back into binders. So if you have an inference variable in the goal, you replace it with an exists. If you have a placeholder, you replace it with a for all. And that's what you do. The way this works is a bit involved. So here's a step-by-step guide, which I guess let's just link to it in the HackMD first. Step-by-step walkthrough. So does it make sense to also look at it in the code? I don't know, don't think so. We have a goal with like two different inference variables, $x, $y, and $y again. So we start by canonicalizing that, which results in exists two types, and well, vec of the first type, friends, trait of second type, and vec of the second type. And the way we do that is by walking, actually, there it makes sense to look at it. So, Rustc. Yeah, that's canonicalization new, cool. That's by folding the type. Oh wait, that's probably not a good link. And yes, it's definitely not a good link. And if we encounter a region which is not bound by so it's not a bound region. So if it's not like a for all inside of the type, we replace that region with a bound variable from which is like bound by the canonical binders, which so there's canonical is only one binder, which actually multiple binders at the same time. That's example time. If we have for all a fn and a that how to actually get an existential insight or for all. For all a 32 trait and like if we have that goal, we would instantiate that binder with the bound variables from that binder with placeholders, because we have to prove it that this holds for all possible A's. We could use that to trait, no, to write that exclamation point A0. And the 0 is the universe of A. And let's say this has a nested obligation which requires that a trait, a soak, other trait, or a soak, with other trait. And for this, we create an inference variable, which is inside of this for. So we would have like question mark, whatever, in the same universe. That's actually universe 1. So we have that. Other trait, or we have a projection goal for this, like to normalize that associate type. We have a projection goal like this. So let's change it up a bit. That's actually this for is it A1? So now we have both a placeholder and an inference variable. And finally, let's also change this to be like exists T. So because exists happens first, that the inference variable for T is in a lower universe than the A. And the reason for that is that this T, like, it cannot name the A, which, God, talk about this unprepared is hard. So another sidetrack. If we have exist T for all u, T is equal to u. Like, this doesn't hold the moment T and u have more than one option, because you can't just set T to u, because at the moment where you would have to decide what T is, you don't even know that u exists. But the other way around, so if you have for all u exists T, if T equals u, this holds. And here you first have a for all, and then the exists is inside of it. So at this point, we already know that u exists. So we can just set T to be equal to u, and this holds. And that's what we need universes for. So because of this, in this example, question mark T0. Question mark T0. If we now canonicalize this goal, we actually get the auto exists for T, because this T cannot name A. And then we have for all A. Oh, let's remain consistent. Okay, I'm not consistent anyways. And then we have another existential inside of it, which is just 0 or whatever. And then the rest of it go with take A, T, and well, I guess U. That's not a lifetime. So, and all of these three binders are all represented just as one canonical. And yeah, I guess that was the original point, that the type Rustc canonical is a binder which like it's actually like multiple binders, because implementing this as 3 nested binders wouldn't be very performant, I guess, and also annoying in Rust. Yes. So anyways, that would be our goal here. And we achieve this by walking over the type of inference variables and placeholders. And whenever we find a region, we always treat that region as if it were an inference variable, for reasons I will not, for reasons for which I have a document on Zulip right now. Oh, it's this document further down. So somewhere in this document, I'm talking about regions, which isn't a good explanation. It will be reworked, it will be in the Rustc dev guide, and then you can look at it. Right now, let's ignore regions for types. If there are inference types, we remember that it was an inference type and replace that with a bound variable, which points into the binders from the canonical. If it was a placeholder type, we also replace it with a bound, like with a bound type. But remember, as part of the canonical, that like as part of this in the canonical var infos, like for each variable bound by this canonical, we remember whether it was a type, whether it was a placeholder type, whether it was a constant, a placeholder constant, or a regions, placeholder regions are also relevant when we return from canonical queries. So yes, so we replace all those with bound variables, and then we have done that. We go to the next step. So we now went from Mac with inference variables to a canonical goal with exists, but the caller will later need to know what these existentials refer to. And for that, we remember the original query values, which are for each bound variable in the canonical, what is the original type from the caller. So we then call the query with only the canonical. So the query itself doesn't know the values from the caller, which allows it to like deduplicate a lot of stuff, because now the values from the caller don't matter anymore. And then inside of the query, we go back from the canonical where we have our 3 binders. Oh, well, here where we have this one binder, and replace the existentials with inference variables again, and the placeholders with placeholders again. But this time these inference variables are, well, they are local to our to the Ztrait-solver, to this current evaluation, and they are local. So we then compute the query. In this example, we figure out that, yeah, this holds for Vec of U32 and trait where there's like a box instead of the question mark of the inference variable 1. So we have to return the constraint somehow that this T0 is has to be U32 and T1 has to be a box of something, so that the caller can actually do something with our result. And for this, when we instantiate the bound variables from the canonical, we also just have a list of their instantiated values, which are the canonical var values. And this list is what we then return to the caller. So we take the list which assigns each canonicalized value from the caller, the value which we computed inside of the query, and then we canonicalize this list again, which happens completely separately from the input canonical. So we get a new existential type, which is now T0, because we just start numbering them from 0, and return this to the caller. The caller then instantiates the returned canonical var values, again with new inference variables and new placeholders, and then equates these with the original query values. So you equate the types from before it canonicalized with the constraints from inside of the query for the canonicalized values, which then constrains x to u32 and y to box of a new inference variable, which results in our final value. And this is a walkthrough of canonicalization, which so yes. Any questions about that, I guess? Apart from, hey, it's a lot. All right. Any other questions, or do you just stop here for today, I guess? All right. So, because the final thing, if you want to help out, there is still a bunch of stuff which we have to do, which can be found by searching for fix me inside of the solver code, which is Rustc trait selection source solve. These fix me's by themselves are fairly unhelpful, because I wrote them so that I understand them in the future, but I know how I want the solver to look like. You probably don't know how I want the solver to look like. So what I intend to do over like this week, probably, hopefully I get to it on Friday, is to open a tracking issue or edit the tracking issue for like each fix me, or at least for each actionable fix me, with a better explanation for how it can be fixed. And then I would definitely love to get some help of that. Yes. All right.